Software-defined power is really a technological leap where we're taking functions and applications that we would normally do bound in a discrete hardware box, and we're instead giving them the freedom to exist in like a software-defined space. A good example of what that looks like is things that have happened in other industries. The telecommunications industry is a great example of this. We went from a discrete device where you can do one form of communication, like a landline phone call, to a form where you have one device where you can do lots of different forms of communication based on the software that exists on that device. Everything from different types of social media contact and communication to different levels of video and voice messaging back and forth to text messaging, and basically anything else you want to do, you just download the right app to do a different form of communication with a different audience or a different type of people. That's basically what software-defined to an application looks like. Similarly, automobiles are moving in that direction as well. You don't need a mechanical function in a car to do everything, every function, every application you want from a car. Now we've got software-defined applications that enhance communication, entertainment, safety, and even providing whole new ways of driving for us. So that industry, you're seeing that move in that industry. That's what we want to happen in the power distribution and power transmission industry for utilities as well. Everything's in boxes now, where if you want to change the function, you have to change the box. In the future, we want to be able to do lots of different things with our power, managing, monitoring, metering, protecting, controlling, automating, and you can do that a lot faster, a lot more efficiently in a software-defined space as opposed to a hardware-defined space. Today, when we're designing substations, there's a lot of things to consider in the architecture. Everything from the price and lead time of the switchgear to the goals of the substation in terms of the functions and applications that you want to perform there, to how you're integrating with the rest of the substation or the rest of your grid. A lot of that being bound by individual electronic devices means you're really limited in like the things that you can choose, the levers you can pull to manage cost, to manage lead time, to manage efficiency and performance of that substation. By going to a software-defined power architecture, a lot of those things become easier. We start to be able to address lead time by standardizing designs a lot more. We can address cost by standardizing the commissioning and testing and installation phases a lot more. We can bring in simulation and digital twins to help improve training time, deployment time, and even to test different configurations before we even have to be on site. We can do complete commissioning setups and testing setups for protection, automation, control functions before we're even at the substation to save you time on site versus in an office. So a lot of that pain points of getting the substation to where it needs to be prior to turning it on, to powering up, we can address in a quicker, more efficient manner with a software-defined power architecture. Today, when we're thinking about applications in a substation, we're thinking very vertical. We're thinking everything from sensing devices to the electronic devices that are performing maybe one or just a couple of functions, to how those are communicating out to a broader network, whether that's your grid management network or an EPMS system, something like that. In a software-defined power system, you're not thinking about it vertically, you're thinking about it more in stacks and applications. So instead of designing for a particular function, say a feeder protection or bus differential protection function, now we can think about a substation in terms of like basic capabilities of the infrastructure. We're going to think about things like the basic sensing devices that are needed and the basic information to perform all of those functions. You're going to think about things we never thought about, like total amount of compute power, like total orchestration for the entire substation or surrounding substations and environments. And you're going to think about cybersecurity requirements as well, but those are just going to be the base infrastructure, and everything will build on top of that. If you have this kind of shell of infrastructure, now you can deposit that with software-defined functions that are applications like you would download on your phone, but except they're going to be on an industrial server or some other type of isolated PC environment or computing environment within the substation. The other thing to think about in this is with this kind of setup, your scalability becomes, I don't know, limitless, really, in the sense of it's only limited by what you might want to do with your facility. You can do this at a lineup, You can do this on an MV or HV side of a substation. You can do it for a whole substation. You could even extend this past the edge into your grid network or into the cloud, and you can have this software-defined architecture defining functions not just for protection and control and metering in a substation, but for asset management for your entire substation or entire grid management. It all can potentially scale into one environment, one platform, just depending on how far you want to take it. But by doing it in a software environment, all of this interconnect becomes much easier, much more straightforward, as well as all the benefits I mentioned before about reducing pain points of commissioning, startup, installation. And on the backside of that, when you're talking about total cost of ownership, the ability to maintain these functions in the sense of firmware upgrades, in the sense of new designs during retrofits, all of that becomes much more possible in a more efficient way because you're upgrading software. You're not having to trade out individual electronic devices, swapping out sensing devices, taking down an entire substation to upgrade or change the functions that you need. All of it's done at the software layer. Much easier to simulate, test before you do it, and then deploy. What we're doing today becomes easier. So I don't want to gloss over that. You can take the designs and the functions that we're doing today and we can do them more efficiently, we can do them in a quicker lead time, and we can manage them a lot better in the long term. So you're saving efficiency and you're increasing reliability just on what we're doing today. But there's a lot of applications that we're trying to figure out how to do, and I think a good example of that is distributed energy resources, pulling in power from renewable sources that are existing and not in your traditional utility grid setup or your centralized generation setup, but in a very distributed manner, trying to coordinate between all of these different environments. Moving to software-defined architecture helps us with that. It helps us because now a lot of those interconnect functions, those communication functions, those protection functions, they exist within the same network. They exist within the same architecture. If you expand, like I was mentioning earlier about scaling that architecture of your software-defined environment, you can expand it not just to a substation, but you can expand it to interconnected distributed resources. Part of this is you're defining open protocols in which to communicate back and forth with different portions of the environment. So, and not just in the terms of the communication, but also in terms of the functions themselves. So you're able to take functions from a substation or from one application and use them, repeat them in other instances as well. The coordination between these kind of complicated coordinated protection monitoring situations between substations and distributed energy resources becomes a lot easier because now you're all speaking the same language, you're using the same architecture, you're using the same components, and your interconnections become much more visible to the customers or the generators or the suppliers that you're working with that you're trying to make these interties with. I'll temper my excitement a little bit to admit we're definitely in these kind of pilot stages, this proof of concept stages. At DTECH here, we're seeing a lot of companies talk about this, and it's really exciting to hear so many different customers, vendors talking about software-defined power in terms of virtual protection, virtualized metering, things like that. But I think we have some really cool things going for us. The investment in grid modernization is huge now and over the next couple of years. And I think that's momentum that's going to carry on in the United States and all the countries surrounding us. The need for power is not going away. The need for more power is not going away. And the need to be more efficient with our power is not going away anytime soon. So the investment, the money that's being poured into the utility industry is big in that sense. And because of that, we have the fervor to do things better, right? And this is a great place that we can start working together between vendors, between utilities, between designers, EPCs, to start working on what does that next generation look like. We're already being forced into it with new forms of generation, diffused or dispersed degeneration activities. Segments like data centers are, pushing us headlong in that sense. There's no choice, right? But it's an exciting time to start exploring this. So how do you start getting into it? You got to start designing for the future. Everybody's going to be working on grid modernization already. It makes no sense to do that with old architectures and the way we were doing it 20 years ago. It makes all the sense in the world to invest money now to prepare ourselves to do that virtualization. And that looks like digital substations. It looks like hybridized digital designs. It looks like in some instances, doing both traditional and digital designs and substation protection control automation today to look at both, start training the workforce to use both, start training operations teams to get used to using both, because it will look different, it will feel different, and we need to take all of us with us, right? It's not just about the engineer, it's not just about the design, but it's also about everybody that's going to be using it in the future as well. And it's the right time to start talking and working with each other and looking at the pilots that other utilities are doing or other vendors are doing and saying, this worked here, this didn't work there, and start adopting the things that work. There's great groups like the VPAC that are already doing that, that are combining between multiple vendors, multiple utilities, and even traditional IT players are coming into the space to help the utility field do that. So I think there's a lot of momentum. I think there's a lot of need and drive for it already, and there's really good collaboration that's starting to build up, and we need to continue to foster that, and we need people at the table that are willing to try new things above all else.